Good evening, this is Michał Wójcik here, or should I say good night, but you don't say good night when you begin your lecture. Well, it's quite late now where I'm sitting, and I went to sleep with the thought that I will present the Lagrangian equations from the least action principle, that I will calculate them from least action principle. The challenge is I didn't prepare any notes for this. I didn't rehearse this. So it will be me trying to calculate Lagrangian equations just from the least action principle, just as I kind of remember this. If I will not remember something, I will try to reinvent it. But come on, I'm a human. I'm a representative of the civilization, the only known civilization in the universe which is able to do differential equations. So it's my duty to be able to do this, whatever time at night it is. So let us begin. First, let us note Lagrangian itself, and then we will try to tell what it means. So we will take a function from R, which is real numbers. Now, I think we will need some open set U and open set V, and that of course will map this into real numbers. Now obviously U and V are just open subsets of some Cartesian product of R, so it's just multi-dimension Cartesian space. Now, what is the idea behind that? So let's consider that we have equation of movement in Rn. So having Lagrangian, we can calculate values from time, position of our, let's say, particle, and from its velocity. And then when we take an integral from some time a to b over this Lagrangian, we will, okay, and this we might treat Lagrangian as a kind of action measure for a point being in this particular situation. So when the particle moves in time, we will require that this integral will be the minimal possible. So it's like the particle is choosing the path or trajectory because it will choose position and velocity. So it's choosing a trajectory which is minimizing this integral. And now, knowing that the particle chooses the trajectory which is minimizing this integral, we will try to calculate the Euler Lagrange equations for L. Let's begin with the assumption that L is of class C1. I hope I will not need to change this assumption later. Right, now, so let's assume we have our path x, we have our trajectory x0, which is minimizing our integral. So let's for a moment, maybe we will need this. Let's just take some letter to denote this this integral from x0. So because x0 will be our trajectory, which is, well, extremizing this integral. I'm just pondering on the name for this j. Let's say j. So j odd x0, well, odd x, however, well, x0 is trajectory, so it's dependent on time, is simply Lagrangian from trajectory and its derivative over time. And we claim that this is extremum. If this is extremum, if we take any trajectory delta x with a property that not this, with a property that delta x of A, which is point in time, is equal to delta x of B is equal to 0, and then we will consider a special function f of lambda, which is equal to j from x0 plus lambda delta x, which is simply, if x0 is a trajectory and delta x is a kind of trajectory, x0 plus lambda times delta x will be again a trajectory. But now, if delta will converge to 0, this trajectory will converge to trajectory x0 in whatever good sense of convergence we will take. This delta, this lambda which is converging to 0, which make this converge to x0, and because AB interval is compact, so I really think it will be a very good convergence, probably uniform convergence, but I will not prove it now. I will just assume it is good enough for us to do a certain assumption. So if that's the case, and x0 extremize j, then obviously f will have extremum in 0. And that means that derivative from the derivative over lambda from f in 0 is equal to 0. Now, is f really differentiable? To verify that, let's think if that derivative makes sense. Right, because we are putting our trajectory, oh, sorry for that. We are putting our trajectory here, dependent on t. At some point we will stop writing this t here. We will just remember it's there. Now obviously derivative is linear, so that will be something like this. And now the question is, can we go with derivative under the integral? And well, this function is continuous because we assume about trajectory to be a nice, probably once differentiable with continuous derivative function. So as our L is of class C1, this whole expression is continuous for both t and lambda, because now this expression depends on t and lambda. T is over the set with finite measure, over the compact set. Derivative over lambda exists, and what's more is continuous. So there is no problem in getting with this derivative under the integral, which is the same as saying that this function is differentiable. So we can safely write this, that if we know that if x0 is minimizing this functional, x0, once again, remind, I'll remind you, this is trajectory. If x0 is minimizing this functional, this integral, then 0 is, I said maximizing, minimizing, extremizing, because we don't know what kind of extremum it is. So then 0 extremize also function f. Right. So in fact, what we know about this is that at point 0, at point lambda equals to 0, this integral vanishes. And now we will start from that. To calculate Euler equations, and I hope I will get to them. I just wonder if not to begin the next page already, but maybe because let's start here and then we will try to move something. So as we said, we can go. I will be just calculating this, knowing that this is 0, and then most likely Euler Lagrange equations will pop up out of it somehow. So yeah, first of all, let's go with the derivative under the integral. Right. Now you will excuse me, I will stop writing t with x0 and delta x, but remember all the time this is a trajectory, so this t is there. We just don't write it just to simplify our equations. Right. So now, once this derivative is here, we need to use the rule of compounding of derivative of the composition of functions for the multivariable functions. I hope I will remember that. So that will be, first we need to start with, you know what, for a moment we will just remember that these arguments will be always after L, so we will skip them and we will return to them at some moment. So now if we we don't need to worry about derivative over t because it is not dependent on lambda. So the first partial derivative that we care about is over x. We will take notation from that. So this is x, and that will be not this symbol, just, and that will be dx over the lambda plus derivative over third argument, which is by convention I will just use this, that this is over derivative of x, but it just means for us that this is third argument. and that will be dx over lambda dt, because we all the time remember this expression is all the time after L. And now let me think about it. If I really no, because obviously this derivative over t is there, but because dt over the lambda is 0, I already neglected that. So let's go further. So we will just calculate this derivatives. So we leave derivative from L over x because we can't do anything with that. Derivative of x over lambda is delta x. How have I written this? X. Okay. And here plus, where is dot? Now it's right. Derivative of L over velocity times the same derivative over time derivative over delta x. And now we need to do a trick. Let us pause with that. Let's remember this, and let's put it on the next board. That was derivative from L over velocity times this small well, not necessarily small, this difference trajectory, or like shift trajectory from the original x0. And now because this dot means here that this is derivative over time. So if we write this like that, now this is just delta x without derivative, and we will calculate time derivative from this expression according obviously to the rules of calculating derivative from multiplication. That will be derivative from the first function I don't know why it is doing this. It's so annoying. I just can't make a dot because it thinks I want to open this menu. So times second function in multiplication, and plus the first function times derivative of time from the second. Now I will need to think how to disable this, but this is so annoying. Right, so we have all I wanted is to express this as the difference of those two, right? So let's put it like that. So let's put it like that. Is equal to minus t okay. And now we can go back to our integral. So let's rewrite this integral on the next board. Okay, from a to b, that was derivative from L over x times delta x plus derivative from L over velocity times delta x, derivative from delta x dt. And now we will replace this summand with this expression. So let's just patiently write it. That will be derivative from L over x times delta x, which is, I still remind you, this is trajectory which depends on t. We just don't write this t to save ourselves a hard labor of writing it. And now we need to put this instead of this term. So derivative over time times delta x minus and it starts to this is wrong. It starts to resemble slowly it starts to resemble Euler Lagrange equations. So I think I'm going into right direction, but I'm not sure yet. I really don't how I will finish that. So bear with me, and we will see. We will see what will happen. Now, look at this expression. What will be integral of this? If we remember the condition which we chosen for this difference, or small, or whatever we will call this trajectory, which we added to x0 and multiplied by lambda, its boundaries at a and b are equal, which simply means, obviously, integral from derivative is just a function under derivative, so that will be a difference between this function from a minus this function from b minus this function from a, which will be 0 because delta x from a and b is 0. So that part disappears. And this is the most important trick that I'm happy I didn't miss. This is the most important trick when we deriving Lagrange equations. Okay, so now we are left with this. And this is a very good position to be. dt. Let me do one more thing, because now we can extract delta x over the bracket. So we will have right, something is wrong here. Something is wrong here, because I should have minus. So let's look if we did this in the right way. So that was this part. So obviously that's minus here and plus here, because we moved this under the other side with minus, so it's here because I inverted that, and this stays with plus at the same side, which means here this will be minus and that will be plus. But nothing changes the argument that we already made, that this expression disappears. So we still have this, but with minus, as we should have. I'm sorry for that. Right, so now we continue with putting delta x after the bracket, minus d over dt Now we will rewrite this now as a full expression. So what we know about this, if we return to the page, to the board back, we know that this at point delta lambda equals to 0 is equal to 0. So this whole expression that we calculated for lambda 0 is equal 0. I will write this explicitly noting here. So yeah, I will write this explicitly using sorry, I didn't want to do this. I will put it here explicitly using lambda, just for you to see where it is, and so it's x0 from t plus lambda delta. Again, the same error. Sorry, this is just how my brain functions. Don't worry about that. Oh, we forgot t. We forgot t. Right. And here the same. Let us be patient and just put it here for this one time. Delta x tab. And derivative. Delta x derivative of t, and this all is multiplied times delta x of t dt. And now we know from the from this that if we put lambda equal to 0, this whole expression, and this was the expression that we transformed all the time, so we get here, so that will be equal to 0. So that equals 0 for lambda 0, which means this part will just disappear. So the equation will be, let's start with integral. We still need bracket. Now it's much shorter because lambda is equal to 0, so it disappeared. Right. Minus derivative over time from derivative over velocity from Lagrangian, t x0 t x t, and now important bit, the delta x at t, because remember this is still certain trajectory, the dt is equal to 0. And now what to do with this? Remember that this works for an arbitrary delta x, because whatever delta x will be chosen here for this function f, because the functional j has extremum at point x0, at trajectory x0, whatever delta x we will choose with this condition, this function which will also have extremum at 0. So that works for any delta x, any trajectory delta x which has 0 at its ends. Now let's rewrite this on the next there should be some option to copy it, but I don't know yet this option, so you will forgive me. I will simply rewrite this on the next board. So once again, integral from AB we forgot t, velocity, minus what I'm doing, derivative over dt from derivative over velocity from Lagrangian, x0 from t, and again velocity times delta x from t dt is equal to 0, but we already said that delta x is arbitrary function. Now, I'm not sure if you remember, but there is a theorem, a mean value theorem for integral, which simply states that if we have continuous function, let's say g, because we already used f, on the from some some interval, I hope continuity is enough here. It should be, because yes, because the integral, the derivative should be continuous, and derivative is always continuous when yes, and derivative will be continuous because we took integral from I'm sorry, I'm just inverting in my head. I'm inverting mean value for derivatives, and I'm just making sure that this that continuity of g is enough. So the point is, there exists some c from AB that this integral is equal to g from c times b minus a. That's a mean value theorem for integral. And obviously, when you remember the mean value theorem for derivative, you can derive this one from that. So, because there is no problem in continuity of this function from t, I mean the whole function, we can apply mean value theorem here, which means there exists some c from A and B that this expression under the integral is equal to 0, because in this case this part will be equal to so derivative over x from t x0 and velocity minus over the time derivative from derivative of over velocity from Lagrangian t good, and this times b. I'm kind of silly because I have written t here, but this is clearly our c, and maybe not c, maybe use something which will be let's use t prime, just to remember this is time. So yeah, so there exists t prime in open interval from a to b such that this expression will be equal to 0. We forgot the most important thing. We forgot the most important thing, which is our trajectory delta x. You will see why this is important. Times b minus a is equal to 0. But because b minus a is positive, b minus a is positive, we can just scrap it. We can it doesn't really matter here. I mean, formally we can divide this equation by b minus a. So in fact we showed that there exists some t prime in a and b, that this expression is equals to 0. Now, a bit of small remark here, a small remark here. What is derivative from Lagrangian over x? X is a multi-dimensional variable, so that will be something like gradient, right? So that's a vector function. That's also vector function of the same number of dimensions. We haven't said that anywhere explicitly, but when we had all these equations, that was a scalar product, because that was from the beginning a vector function, and that is also vector, right? Because the trajectory in multidimensional space has argument is time, but values are multidimensional of the sufficient dimension. So these were all scalar. These were all a scalar product. So we have scalar product here. So because this is arbitrary, delta t is arbitrary, we can set this to 1, but we can set this to 1 on each of its coordinates. So in fact, we can create here a system of equations. And sorry, I was not prepared for that. I simply forgot these are multidimensional, and I'm improvising now. So because delta x is arbitrary, we can always have that at time point t prime, it will have value this or this or this and so on up to one on the last coordinate. What this will give us? That will give us exactly this equation, but for each coordinate of this vector function separately, which in effect will give us one equation that we can write in, again, in vector notation, t prime x0 from t prime velocity over x0 from x0 is equal to 0. So once again, what have we done here? That was number. That was a real value, because here is a scalar product. Now, because delta x is arbitrary, we can always choose it that for the point okay, I hesitated here because t prime exists for a, so delta x already exists, and then we are choosing t prime. So the trick needs to be stronger here. Let me just think about it. Because yes, we can still request this, but our delta x must be equal 0 at the boundaries. So what we need to do is we need to do something like this. It very quickly needs to reach the level of 1 in each dimension. But then still t might be somewhere else. But okay, let me withdraw from that. Let me withdraw from that. We will do a simple correction here. So our delta x from t will be, so we will take n functions, right, this might not yet, forgive me, that can't be t, that must be a function. Okay, so let's assume we have any function f which do something like that. This is a, this is b. I just don't want to now invent the equation, but the point is it has 0 in a, 0 in b, something positive in between. Not f, because we already used f. So let this be h, or no, I don't like h. V. Function v, which has this property that with in a it has 0, in b it has 0, value are zeros, and it's positive everything in between. So we will take here vt right. So now the argument I wanted to make will work. So for any arbitrary trajectory delta x, we will have this t prime, which will for which this expression will be equal to 0. Good. Now, if for any, then we will choose these n functions delta x. Each of them has a function v of t on one coordinate, and the rest of coordinates is 0. So this is a perfectly good trajectory which has 0 at e, 0 at b, something in between, which is moving only in one dimension, but it's perfectly valid. We will request from that function to be differentiable, so that's fine. And now, by doing this, each of these equations will give us this times vt. I will erase it here. This in bracket. V at t prime equal to 0, right? Because the scalar product will only contain this summand, because all other will vanish, And as we take n trajectories, as I described them here, each of them will give us equation for different coordinate, which means for a different partial derivative. And obviously t prime is different for each of our trajectories delta x. But because it belongs to the open interval from a to b, this value is positive. If it's positive, it means that this part is equal to 0. If that's true, that means that the whole vector, so if we go back to this expression when derivative is a vector because it's a derivative over multi-dimension variable, then we can go back to this vector and it is equal to 0 because here we show that each coordinate is equal to 0. So here I would just x 0 no, because t prime was different each time. So we proved for a different. Okay, fine. We will deal with that. We will deal with that. Sorry, just not so quick. Just not so quick. Just not so quick. So what we proved in fact is that for each coordinate e, for each coordinate e, I'm sorry, that's from Polish. From each coordinate I, there exists t prime that this is equal to 0. We don't make any assumption t is the same. So we have only this. We have only this for some t between a and b. But we proved that for any a and b, because a and b might be arbitrarily chosen, for any coordinate there exists such a time t prime that this expression is equal to 0, which means, well, we can scrap that because we know it's positive. This is equal to 0. Okay, our little problem is that t prime is different for each coordinate. How we will deal with that? Well, we can request that B converges to A. And now, obviously, t prime is always between. So t prime also converges to A. But our Lagrangian had continuous derivatives. So this function over t, and here is the point that we need to request. Here is the point that we need to request that this is also continuous. So we need to request that L, we need to go back and request that t in fact is second, has all second derivatives, not all, but just the easiest things to do. We need to remember that only second derivative over t over velocity needs to be continuous, but we need this assumption for this. I just wonder if we really need this assumption, or if this is just a problem of my proof. But yes, once this is all continuous, we know do we? Because it's for all, we reason for all coordinates separately. Yes, but this is the function continuous in all coordinates. So if by continuity we will prove this for each coordinate separately, we will prove then on each coordinate this equation holds for A. And A can be also chosen arbitrarily. So by using these arguments, we are showing that this I forgot that I am here, so I need to look into the second screen. Right, and this is the same. This is the same as here. I need to be brief. Yeah, I fit this. Right. So by this reasoning with convergence, we can prove that for each coordinate, the partial derivative of this and this, which is just the Euler Lagrange equation, is equal to 0 for A. But in the whole reasoning, A might be chosen arbitrarily, because there is nothing particular when we have chosen AB. The whole reasoning will go for any AB. Obviously, we used already that B was arbitrary, but now we can use that A is arbitrary. So in that case, we have proven for any t Euler Lagrange equation, because if we set this on each coordinate to 0, obviously the whole vector will be 0. So let's put it somewhere here. The equation that we proved. And it is Euler Lagrange equation. So all was pretty clear till that point when we used average mean valued theorem to get this t prime. then we realize that t prime depends on the choice of delta x. And we realize that this is scalar product. So we needed to use n functions as delta x. Each of them had only one coordinate non-zero with this function v. That gave us that for each coordinate we found some t prime which made this equal to 0, but that was just for coordinate. Then again, for each coordinate separately, we did this argument, we requested B converges to A, and then obviously again for all this kind of B we had this t prime according to the previous reasoning. So effectively t prime converges to A as well, and because this expression is continuous, which required additional assumption over L for L, so having this continuity, we can state that the derivative over this coordinate from time A here is equal to 0. And because A is also arbitrarily chosen, that works for any t. So in effect, we have this equation for any x0 which is an extremum of our integral, of this integral that we started. If x0 is an extremum of that integral, this equation holds. And with this small caveat, which is that we needed to request it continuity of derivative over x over velocity, and then over t, we needed to request continuity of this. That reasoning holds, I think, and it's rather strict. I don't think there is any particular hole in this. So yeah, I think that's good. I will look into that later. But I really think at the moment I think I did it with this small caveat. But I will check in my books if we really need to request this condition, if there is any way to avoid this. So it's done. It's done. Sorry for a moments of confusion, because as I said at the beginning, the purpose was to do this without preparations, without any notes, just as an experiment. Right, let me know what you think, and goodbye. It is good night for me. Good whatever other part of the day it is for you now. And see you later. We have Euler Lagrange equation derived. Thank you.